Assalamu alaikum. Hello, welcome back. We are back for another exam review. Can you believe how fast the year has gone by? Well, what we're going to be doing today is we're going to be answering the review packet questions. So please have your paper and pen and calculator ready, obviously. What I want you to do is go through the questions with me as I go along. So you pause the video, solve the question, and then obviously check your answer with me as I solve it. And try and relax. Try and just have a nice, safe, relaxing environment where you're comfortable, away from noise, where you can focus. This is my safe space. This is my office. I have a bit of popcorn that I'm going to reward myself with every once in a while. So be comfortable. Let's get on with it. This is obviously the recommended book for the course, and these are the topics that we're covering today: work and energy, as well as conservation of energy, collisions, momentum, and conservation of momentum. These are the formulas you should be familiar with. I do want to make a note here that power is equivalent to work over time, but it's also equal to change of energy over time as well, because work and change of energy are both synonymous, interchangeable terms. We also have impulse here, and impulse is force times time, but impulse is also equivalent to change of momentum, or final momentum minus initial momentum, as well as final mass times multiplied by the final velocity minus the initial velocity. These are things you're obviously familiar with, just in case you've forgotten about them. As we go along with the questions, I'm sure most of this stuff will come back to you. Okay? So, oh yes, of course, the definitions that you need to be familiar with as well. So obviously this portion of the course, these are the terms that you should by now hopefully be very, very familiar with. Okay, sorry about that. Zooming in and out. Here we go. So this is the terminology that you need to be familiar with. Okay. Work, impulse, elastic, potential, energy, power, momentum, conservation of energy, kinetic energy, force, elastic collisions, as well as inelastic collisions, gravitational potential energy, spring constant, and friction. So I'm sure most of you by now know these inside out. Okay, let's get on with the problem solving portion of the video. So as I said, please have your pen and paper ready and your calculator as well. So pause the video, try and solve it yourself, and then solve it, and then check your answer with me. Right, so we've got a 75 Newton force is applied at an angle of 20 degrees to the horizontal in order to move a 25 kilogram box a distance of 3 meters. Calculate the work done. So obviously the force is being applied in the horizontal direction, i.e. in this, oops, I've got that upside down, this way here. And so we need not to worry about this force over here. We only need to worry about this force over here. And as such, we can use this formula. Work is equivalent to force times distance multiplied by cosine theta. So what do we have? We've got the force right here, so that's the force, 75. We've got the distance as well, 3 meters. And we've got the cosine of theta, yeah, it's 20 degrees. So we actually have everything that we need, so it's a pretty easy question. If you get this one on the exam, that is a pretty easy question. Let's have a look. So that is going to equal 211.4 joules. Okay? So that's the answer to that one. Okay, let's keep going. A weightlifter lifts an 80 kilogram barbell to a height of 1.8 meters in 2 seconds. Find the force exerted, the amount of work the weightlifter did, and the power he exerted. Okay, so obviously this is a male weightlifter and he's lifted a barbell. We need to find the force, we need to find the amount of work, and we need to find the power. So those are 3 different things. Let's start with the force, okay? So the force is going to be in the y direction. So that's going to be the weight force, right? And of course we know that weight force is going to be mass times gravity, which is going to equal, sorry, just a second. So that's going to equal mass times gravity, which is going to equal 80 multiplied by 9.81. So the force is going to be nearly 77. 80 times 9.81, which which is 784. 784.8 newtons, obviously, because the force is measured in newtons. Let's have a look. What else do we have to work out? We have to work out the work. So the work is equivalent to the force times the distance, and that's going to equal, the distance in this case is 1.8 meters, so that's given. So force is, we just worked it out, 784.8 newtons multiplied by a distance of 1.8 meters, and that's going to equal 1412.64 joules. Now, there's a note to be made here, and that's the fact that I'm not rounding up just yet. And the reason why I'm not rounding up just yet is because we're still using those numbers. So it's always good practice not to round up during the workout, because obviously the error will be cascaded. So what you need to do is just wait till the very end to do the rounding. Finally, we need to work out the power, and power is equivalent to work over time. So we've worked out the work, so that's 1412.64, and we know the time, 2 seconds. That's how long it took them to actually lift that. So it's going to be that divided by 2, and we're back to 706.32. And what's the unit of power? What is the unit of power? It is in fact watt. So 706.32 watt, or if you prefer, 706 watts. Okay, and that's how you solve that one. Let's keep going. A forklift worker raises a 50-kilogram crate from the ground to a shelf at a height of 2.2 meters. If the process took 20 seconds, what was the average power the lift exerted on the crane? So once again, we need to find the work, and work is equivalent to force times distance. The reason why we don't have cosine theta in this case is because there's no angle. It is in the same direction as the movement, and so since the force is in the same direction as the movement, we don't have to worry about the angle, and as a matter of fact, there is none. So work is equal to force times distance, and that's going to equal, I need to change the color. I'm not very happy with this color. Let's go with the blue. We'll go with pink. Purple. Let's try purple for a bit. Force times distance, so that's going to be 50 kilograms, because remember the force is going to be mass times gravity. So you got to work out that first. So 50 times 9.81, and once you work out the force, then you multiply it by the distance, right? So that's going to be 50 times 9.81, which should be about 480, 490.5, 490.5, and then we'll multiply that by the distance, which is 2.2 meters. Now that's going to give me the work. So the work in this instance is going to be 1079.1. Oops, that is not very nice. There we go. And of course it's joules. Now next what we need to do is work out the power. And so power is equivalent to work over time. It is the rate at which you've done the work. So it's going to be 1079.1 divided by 20 seconds. And that is equivalent to 53.955. Obviously we need to round that. So 54 watts. That's the answer. Okay, let's keep going. Here we go. A woman lifts her 100 Newton child up by 1 meter and carries her 50 meters to the bedroom. How much work does the woman do? Well, it's not a very nicely worded question, and what I mean by that is it just says how much work does the woman do. I can no longer use. Oh, here we go. We're back. So the assumption here is that they want to know the amount of work she's done in the vertical direction, on the vertical axis, because they haven't given us anything about the horizontal axis. So how much work she's done is going to be simply work is equal to force times distance. What is going on here? That's never happened before. Very interesting stuff. Force is equal to work is equal to force times distance, which is equivalent to 100 multiplied by 1 meter, and that's going to be 100 joules. Now you might be wondering, what about the 50 meters? Well, that means nothing because we don't have the force that is acting in the 50 meters. We just, since she carried the child, she's done some work because the force is acting in the same direction as the distance. But in this instance, when she's moving horizontally, there is no work done that way. So it's just 100 joules. Okay? Let's move on. Question 5. We're doing very well. A mother lifts each of her twin babies 1 meter straight up. Each baby weighs 90 newtons. How much work does she do? So once again, work is equivalent to force times distance. So we've got 90 newtons multiplied by, oops, we're doing that thing again. 90 newtons multiplied by 1 meter, and that equals to 90 joules. But this is not the final answer because she's got twin babies. Make sure you read the question carefully. Twin babies, that means we have, so another part to the question. So it's going to be 90 joules multiplied by 2, and that equals 180 joules. Now you don't have to do it this way. You can go 90 joules plus 90 joules. You can just go 90 times 2 multiplied by 1. So there's 3 or 4 different ways you could do it. So that's fine. Okay, let's move on to question 6, and we're back to an example with an angle. A 100 Newton force is applied at 30-degree angle to move a 15-kilogram object. That is just red herring. You don't need to worry about that. 5 meters across the floor at constant speed. How much work is done? Okay, so once again, work is equivalent to the force applied multiplied by the distance. But since we have an angle here, we need to worry about this angle. So it's times cosine theta. So the amount of work applied is 100 newtons, and that's applied directly downwards. So that's 100 newtons multiplied by a distance of how much? Okay, we've got 5 meter distance, right? And the cosine of 30 is going to be, that's 86.6 multiplied by 5 multiplied by 500. And so the work done is going to be equivalent to 433 joules. Okay, and always check your units. And remember, the way we answer these is we write the formula, we show the workout, and we put the answer with the units. Okay, don't forget the answer and the units. A man pushes a lawnmower using 900 newtons of force at an angle of 60 degrees below the horizontal. Okay. 60 degrees below the horizontal. Interesting. If he pushes it 30 meters, how much work does he do? Okay. So that's, once again, the same sort of example. Work is equal to force multiplied by distance multiplied by cosine of theta, which equals 900 multiplied by 30 meters multiplied by cosine of 60, and that's going to equal 900 times 30 times cosine of 60. Oh, that's a nice number. 13,500 joules worth of energy. Bit of a workout. Okay, a weightlifter lifts a 95 kilogram barbell up to a height of 2 meters in 1.5 seconds. Find the force applied. Force applied is equivalent to mass times gravity, since we are talking about a vertical direction here, the y-axis, so it's going to be 95 multiplied by 9.81, and that's going to equal 930, maybe 931.95 newtons. Part B, we need to find the work. So work is equivalent to force times distance. We've just worked out the force, so it's going to be 931.95 multiplied by 2 meters. So it's just twice that. So 1863.9 joules. And finally, we're asked to work out the power, and the power is going to equal the work over the time. So that's going to equal 1863.9 all over the time, which is 1.5 seconds. So it's going to be 1242.6 watts. And that's the answer. Okay, we're doing quite well. Doing quite well. Let's keep going. A 1.25 kilogram textbook is pushed a distance of 65 centimeters with 3 Newton force to the right. Friction is 2.5 newtons to the left. What is the total work done on the textbook? Okay, so immediately I'm noticing something, which is that is in centimeters, and remember, we don't work with centimeters, we work with meters. So the first thing I need to do is change the centimeters to meters, and the way I change centimeters to meters is divide by 100, okay, because there's 100 centimeters in a meter. Okay, so that's going to be 0.65 meters. Okay, so that's the first thing you should do. If you see grams, you change it to kilograms, and if you see centimeters, you change it to meters. The other thing I'm noticing is in the question it says 3 newtons to the right, and over here it says 3.5 newtons to the right. So I think what happened here was somebody just sort of changed their mind last minute about the parameters, which is no matter. So let's have a look. So that we'll just change it to 3 newtons as it was. And so what we need to do first of all is work out the net force acting on the box. So the net force is going to be force, oops, I don't like the way it does that. Makes me force net is equal to plus 3. If we take the right as plus and then the left as minus, then we can work out the net force to be plus 5, or newtons to the right, obviously. So then what do we do? And you don't have to take positive as being right or negative as being left. You can swap them around as long as you stay consistent with the final answer. So now we've got the net force. What do we need to find? What is the total work done? Okay, so work is equivalent to force times distance. What was the distance pushed? So 0.65. So we've got 0.5 times 0.65, which is equivalent to 0.325. 0.65, and that is 0.325 joules. And that's all you need to do. Okay, easy. Okay, let's keep going. Rank the following rock climbers from greatest to least gravitational potential energy. Okay, so what we need to do here is obviously know the formula for gravitational potential energy, which is GPE is equivalent to mass times gravity times the acceleration towards gravity multiplied by height. So we need to do that for each one of those. So the way I would do it, and you don't have to do it this way, but this is the way I would do it. For my neighbors upstairs are being a bit noisy. My apologies about that. For the 49 kg climber, okay, it's going to be GPE is equivalent to mgh, which is equivalent to 49 multiplied by 9.81 multiplied by 30, and that's going to give me a number. Okay, so 49 multiplied by 9.81 times 30, and that's going to be 1,442 point, oops, no it's not, it's 14,420.7 joules. Now I'm not going to write that whole sentence again. What I'm going to do for this one is I'm going to go GPE, and I'm going to do 54 kg, and that immediately tells me that it's the 54 kg climber. And it's going to be 54 multiplied by 9.81 multiplied by 25. 54 times 9.81 times 25, and that's going to equal 13,243.5 joules. And finally, GPE for the 62 kilogram climber. Once again, we have to multiply the mass by the gravitational acceleration, or acceleration towards gravity, multiplied by the height. So it's 62 multiplied by 9.81 times 24, and that is 14,597.28. Now, we haven't answered the question yet. It says rank the following climbers from greatest to least gravitational potential energy. So we need to actually rank them. Okay, so just giving me the workout on its own is not enough. You have to rank them from greatest to least. So the third one is actually the most, and then the first one is the second, and the third one is the middle one. Okay, so that's how you do it. Right, I'll see you in just an instant. Okay, and we're back. So let's keep going. What are we up to now? Here we go. A cart of mass 700 grams. Okay, so first of all, remember what I told you. If it says grams, change it to kilograms. So that should be 0.7 kilograms. How do I know that? Because there are 1,000 grams in a kilogram. Okay, so you divide by 1,000, sorry. So a 0.7 kilogram cart is attached to a spring and compressed 15 centimeters. So once again, I have to change that to 0.15 meters because I have to divide by 100. The spring constant is 120 newtons per meter. What is the cart's velocity as it passes through the equilibrium position, which is the starting position? Okay, so here we've got an energy change or energy transformation kind of problem. To begin with, we have to understand that elastic potential energy is equivalent to kinetic energy in this instance. Okay, so elastic potential energy is equivalent to kinetic energy. And so elastic potential energy has a formula, and that's half kx squared. Now, it could be x, it could be e, depending on the book, but they're exactly the same. And I like to use x, and that's what you're going to see in the formula sheet. Is equivalent to half mv squared. So what we need to do is find the elastic potential energy, and once we find the elastic potential energy, we've essentially found the kinetic energy, and we can find the velocity. So step one, find elastic potential energy, which is half kx squared. We've got the k, which is 120, and we've got the extension, which is 0.15, and that's going to equal 60 times 0.15, which is 9 joules. So once we've found that, what we can do is say, okay, so we know that elastic potential energy is equivalent to kinetic energy. So we also know that half mv squared, which is the kinetic energy, is going to equal 9 joules because we've just worked it out. And so half multiplied by 0.7 multiplied by v squared is equivalent to 9. V is therefore the square root of 9, that, the right hand side, all over half times 0.7. Okay, so 9 divided by, which is 1.6. Did I do that right? 1.6 meters per second. I realized the mistake that I've made. I went there. There's the mistake. It's squared. Please don't make the same mistake I have. So 0.5 times 120 times 0.15 squared, and that equals 1.35. And so, okay, so that equals 1.35, and that equals 1.35. And so it's going to be 1.35. 1.35 divided by 0.5 times 0.7, and then square root of the whole thing, and that's equivalent to 1.96 meters per second. Okay, so that's the answer. My apologies about that mistake that I made earlier. Right. Number 12. A 2.7 kilogram bag is dropped from an 11 meter drop height and is caught 1.7 meters above the ground. Find the bag's speed just before it hits the ground. Okay, so we need to know the distance it traveled. And the distance the bag traveled is not measured from the top of the bag all the way to the ground. It's the distance it travels. So it's from here to there. So it's 11 minus 1.7. Okay? So it's 9.3. Because that is going to be how much energy it has. It's the distance it has traveled. So it's going to be, first of all, gravitational potential energy is equivalent to kinetic energy in this case. And that's mgh is equivalent to half mv squared. So let's work out, step one, let's work out GPE. So that's going to be mass times gravity times height, which is equivalent to 2.7 multiplied by 9.81 multiplied by 9.3. That's the height. So 2.7 multiplied by 9.81 multiplied by 9.3, and that's going to equal 246.3 joules. Now what we need to do next is find out the kinetic energy. So the kinetic energy is going to equal that because we've just worked it out. So half times mass times velocity squared is equivalent to 246.3. We have the mass as well, that's 2.7. So we know that V is going to equal the square root of 246.3 all over half times 2.7, and that's going to give us 13.5 meters. Okay, let's keep going. If you've noticed that my shirt changed, it's because it's the next day. Let's keep going anyway. A 0.12 kilogram ball is launched straight up from a spring-loaded launcher. The launcher is 1.9 meters high. The spring constant is 280 newtons per meter, and it's compressed 19 centimeters. So what is the ball's speed when it reaches a height of 2 meters? So the way we solve this, okay, for these questions, I really want to explain things in a little bit more detail just so you're aware of what to look out for. So the first thing we need to do is figure out what is the question asking, and the question's asking for the speed. So we need to find the velocity, yeah, when it reaches 2 meters, okay? So first of all, that 19 centimeters, we need to change it and make it 0.19 meters, okay? Because remember, we only deal with meters and kilograms. So let's have a look. What is happening here is that the energy is being transferred from the spring, elastic potential energy, into, and it's going to what? It's going to kinetic energy as well as some gravitational potential energy, because of course as the ball is gaining height, the higher up it goes, the more gravitational potential energy it's going to have. The other thing as well, the other thing as well is as the ball leaves, most of that energy is going to be kinetic energy right at the start, because it's obviously starting to move. So let's see. The first thing we need to realize is that all the energy is coming from the elastic potential energy. Elastic potential energy has a formula. So elastic potential energy is equivalent to half kx squared. Remember, x is the extension. So then we can work out that it's going to be half multiplied by 280, that's just from the question, that's the spring constant, multiplied by 0.19 squared. Now don't forget, it's the squared part that people forget, including myself. So it's 0.5 times 280 times 0.19 squared. So I've got a little bit of a confession to make about this question. This is the kind of question that can be quite confusing. I've confused myself and my colleagues as well doing this question, because I've changed my answers like 2 or 3 times. Yusuf knows I have done that. Now the reason being is because it was a discussion that we had whether we go with 2 meters as a height or 0.1 meters as a height. If you don't know what I mean, I'll explain in a minute. So now I've worked out the total kinetic elastic potential energy. What I need to do next is work out the gravitational potential energy, and the reason why I'm doing that is because I'm not interested in it, and this might seem a bit confusing. Well, if you're not interested in it, why are you working it out? Well, I'm interested in eliminating it. So I don't want the gravitational potential energy, and I need to get rid of it. So what I need to do is figure out that this here, kinetic energy, is going to equal elastic potential energy minus gravitational potential energy, because the ball is gaining height, yeah? So I need to reduce that. I need to remove that. So this is where, okay, well, we've got the elastic potential energy right here. We've got a numerical value for it. So it's 0.054 minus the gravitational potential energy. Now here's the thing. This is where the confusion happens. You see, gravitational potential energy has a formula, and the formula is mass times gravity times height. And this guy here, that's where all the confusion was, okay? What height do we use? Well, it's quite simple, really. We use the height that the ball traveled, and I've said that so many times in class, and yet somehow managed to confuse myself a few times. So that's what we need to do. We need to use the height that the ball traveled, and not the total height, but the height that it has traveled from. So we treat this as the new ground in a way, okay? And so it will be gravity, m, the mass 0.12, multiplied by 9.81, which is the acceleration due to gravity, times 0.1. And so that's going to give me 4.9363. Now I'm not rounding up too much at the moment because we're still working it out. Now I've just worked out kinetic energy, which is great. Now we're 90% of the way there now. So what I need to do next is work out the velocity, because that's what they're asking for. So it's going to be the kinetic energy is going to equal half times mass. Oops, let's change that v into an m. Mass times v squared, and so it's going to equal half multiplied by 0.12 times v squared for 4.9363. Now notice that's really close to 5. The reason being is because the ball only traveled just a little distance. It only traveled about 10 centimeters. I mean, the difference between 2 meters and 1.9 meters is 10 centimeters literally. So obviously it's just left that spring and it's traveling upwards. So that's only 10 centimeters. Obviously it's not going to be a lot of gravitational potential energy. But yeah, anyway, 4.9363, that's the answer, divided by 0.5 multiplied by 0.12, and that gives me v squared. All right, so v squared is equivalent to 82. Square root all of that, and that is going to be 9.1. Okay, so I can actually rearrange this just in case a student asks me, how'd you get v? V is going to be the square root of this over that. Okay, so it's going to be 4.9363 all over half times 0.12. And so v is equivalent to 9.1 meters per second. Okay, we're doing well. Let's keep going. Question 14, you drop a 6.3 kilogram bowling ball from, I'm going to change the color too though, because plum. Let's go with dark gray for a change. See how that fares out. You drop a 6.3 kilogram bowling ball from an 8-meter high tree house. Oh, I love tree houses. It lands on a trampoline 75 centimeters above the ground. So this trampoline here is 75 centimeters above the ground. Okay, so it's 0.75 meters. Remember, we don't deal with centimeters, we deal with meters. The trampoline stretches down 0.6 meters. So this is going to cause the trampoline to stretch down. Oops, maybe I should have used a different color. Okay, so this is going to use this is going to cause the trampoline to stretch down 0. Oh, that's a terrible color as well. Let me try and see if I can find a color that. Yeah, we'll go with light green. Okay, so it's going to stretch down like that. Okay, and that distance down, that is 0.6 meters. Okay, so that's what we're talking about over here. So that distance here is 0.6 meters. Okay, the trampoline stretches down 0.6 meters before the ball stops completely, okay, which is an unusual scenario, but for the sake of this question, that's what's happening. It stops completely. Find the spring constant of the trampoline. So we're looking for K, right? That's the first thing we need to figure out. What is K? That is what the question's asking for. So just so you don't get confused. So what is happening is we've got gravitational potential energy, because that's where the energy is coming from. The ball is being dropped. It's not being pushed. It's being dropped. So we've got a lot of gravitational potential energy that's going to be transferred into elastic potential energy. So we need to work out gravitational potential energy. And gravitational potential energy is equivalent to mass times gravity times height. Do we have the mass? 6.3 multiplied by 9.81. That's the acceleration towards gravity. And multiplied by the height, which is, what height do we use? Now that is an interesting question. How much has the ball traveled? The ball has only traveled this much. So it's going to be 8 minus 0.75, which is 7.25. Now, why don't we use the 8? Well, because that's not the distance that the ball traveled. Imagine if I say, for example, that this whole scenario, this whole tree house is sitting on top of a cliff, right? And the cliff is, say, 30 meters in height. Do I then use 30 meters? No, it doesn't matter. I just use the distance the ball traveled. So the ball travels 7.25 meters, and that's all that matters. It doesnn't matter that it's an 8-meter tall tree house. All I need to worry about is the distance the ball traveled, okay? So that's why it's only 7.25. I think that's the trickiest part of the question, is figuring out the height to use. So 6.3 times 9.81 times 7.25. So that gives me the total gravitational potential energy, which obviously is the same as the elastic potential energy. So that's what that is. So now once I've figured out the gravitational potential energy, I've worked out the EPE, because that is what that is. That's I'm just gonna write that same as EPE. I've managed to go back to dark blue. Just I guess I must like it a lot. Kx squared. I've got that. So that's 448.1 joules. Half times K times what's the stretch? 0.6. Remember, it's not 60, it's 0.6 squared. And so K is going to equal 448.1 all over half times 0.6 squared. Okay, you can also use the function of shift solve in your calculator, but I always like to do it the good old-fashioned way. So the value of K is going to equal 2,489 newtons per meter. Okay, and that's how we do that one. Okay, we're up to 15 now. An airplane with a mass of 125,000 flies at 220 meters per second at a height of 8 kilometers. What is the total energy of the system, kinetic and gravitational? Okay, so we've got two types of energies here. We've got kinetic energy, which is the energy of motion, and that's going to equal half times mass times velocity squared. We also have gravitational potential energy, and that's going to be the mass multiplied by gravity multiplied by the height. And it doesn't matter which one you work out first, but we need to work out both, and the total energy of the system is going to be the summation of both energies. That means the addition of both. So it's going to equal half multiplied by 125,000 multiplied by 220 squared. That's going to give me the total kinetic energy, which is going to be a huge number. And rightfully so, because we're talking about an airplane here. Okay, now normally I would use scientific notations. However, just for visual simplicity, I'm going to put it this way. And that is going to equal, now we're working out the gravitational potential energy, so that's 125,000 multiplied by 9.81. Let me just fix that. Multiplied by the height, which is 8 kilometers. Now remember, we don't deal with kilometers, we deal with meters. So it's going to be 8,000 meters, because 8 kilometers is the same as 8,000 meters. And so the gravitational potential energy is going to equal another big number. Wait, where's that? Times 8,000. That is massive. 981,000,000,000. Quite a few zeros. Okay, so those are the numbers we're dealing with. So total energy, which is mechanical energy in this case, of course, as you know, because mechanical energy is both the summation of kinetic energy and gravitational potential energy. So the total energy is going to be Ke plus GPE, which is just adding those two numbers together. So it's going to equal 1.28 times 10 to the power of 10 joules. And you can write it using scientific notations, or you can just write it all out if you want to. Okay? Right, let's move on. A person who's 58 kilograms jumps on a trampoline, compressing it by 40 centimeters. The spring constant is this much. How high does the person bounce above the trampoline? So when it says how high does the person bounce, we're looking for h. That's what we're looking for. So that's the first step, is to figure out what the question's asking, right? So since we're looking for h, and I know that's what we're looking for, it's just going to make things a little bit easier just pointing that out right at the start. Where's all the energy coming from? The energy is coming from elastic potential energy. So that's where it's coming from. Elastic potential energy is going to be, because the spring is compressed and then it launches the person upwards. So it's half multiplied by k multiplied by x squared. Remember, x is the compression. So it's going to be half multiplied by 1250 multiplied by 0.4 squared. 0.4, why is that? Because it's 40 centimeters, so it's 0.4 meters. And that's going to give me a number, 0.5 times 1250 times 0.4 squared. And that's going to be a nice, beautiful 100 joules. So then what do I do with that? Well, I know that that's also equivalent to the kinetic energy. Okay? Oh, sorry, not kinetic energy. Gravitational potential energy. Because once that person is bounced up, right there at the top, there's no kinetic energy. Remember when you throw something upwards, and right at the top of the path, of the flight path, that object is no longer moving. It's got zero kinetic energy, and it's just sort of momentarily right there, stuck in the air. At that point, it's at its highest point, and it's got zero kinetic energy, and it's got the maximum gravitational potential energy. Now that's the point we're talking about here. So that's the same as gravitational potential energy, or should we say maximum gravitational potential energy. So GPE is going to be equal to mass times gravity times height. Whoops. There we go. So 100 is equivalent to 58 multiplied by 9.81 multiplied by the height. So obviously, therefore, the height is going to equal 100 all over 58 times 9.81. So it's about, wait a minute, what have I done wrong? 9, 8, C. Oh, here we go. 100 divided by 58 times 9.81. Here we go. That's more like it. 0.176 meters. Or 17.6 centimeters. Or if you prefer, 0.18 meters. And that's good enough. So 2 significant figures is fine here. Okay. Right, let's move on. A 750 kilogram roller coaster car starts from rest at the height of 90 meters. What is the speed at the top of the second hill that is 75 meters in height? Multiple ways of doing this. The way I would do it, let me just zoom back in again. The way I would do it is, first of all, I have to give it a bit of thought, yeah? You have to think about what's going on in this question. What's going on in this question is I've got a roller coaster cart that's right at the top of the hill, of the first hill, and that's all the energy from there is going to be gravitational potential energy. So once I know that, I also know that on the top of the second hill, there's going to be a lot of gravitational potential energy, but there's also going to be some movement, so there's going to be some kinetic energy, right? So let me just show you what that looks like on the actual diagram, and this time I'm going to use dark green. So over here, I've got pure and simple gravitational potential energy, and I'm just going to call it 1 for the first hill. Now over here, I'm going to have gravitational potential energy as well, but that's going to be 2, and it's going to have some kinetic energy, and that's what I'm interested in, because the kinetic energy is going to tell me about the velocity that I'm after here, the speed. Okay, so what do I need to do? I need to figure out, first of all, I need to work out GPE1, because that's going to tell me the total energy, which is going to be mass times gravity times height. Once I figure that out, I can eliminate, or I can take away GPE2, and that way I can be left with kinetic energy. So GPE1 equals mass times 750 times 9.81. So that's going to be 750 times 9.81 times 90. 662,175 joules. Now I've worked out what GPE1 is going to be. Now what I need to do is work out GPE2. So that's step 2. GPE2, which is the gravitational potential energy that the cart's going to have on top of the second hill. So once again, formula, workout, answer. So it's going to be 750 times 9.81 times the height, which is 75. And that's going to be a bit smaller, and the reason being, of course, is because it's a smaller hill. We're ignoring resistance and all of that for this question, obviously. Now, kinetic energy on the second hill is going to be equal to GPE1 minus GPE2. Reason being, of course, is because that's the total energy, and then that's how much energy was lost in gravitational potential energy form. So what's left is going to be kinetic energy. So that's going to equal 11,000? Nope, 110,000. Oops. 362.5 joules. So let's see. What do we do there? What do we do now? What we do now is we go, oh, hang on. We know that that number is equivalent to half times mass times velocity squared. We're looking for the velocity, so we know that it's going to be v is equivalent to the square root of 110,362.5 all over half the mass, which is 750. That doesn't look very clear, does it? Here we go. Slightly better. And so the speed is going to be I'm getting 5.4 meters per second, which seems a bit low, but there you go. Let me just do a quick check. See, what did I do wrong? Let's see, 110,362.5 divided by 0.5 times 350, times 750. Oops. Yeah, I see the mistake I made. Oops. So that's going to be 17.16 or 17.2 meters per second. Always pays to have a rough idea of what the answer should be in your head, like just from a common sense point of view. And so that way you kind of doubt yourself, and it's kind of like a checking point. So rather than just going, okay, that's the number, that's the answer, does it make sense? Ask yourself, does it make sense? Is it positive when it's supposed to be negative, or is it negative when it's supposed to be positive? Is it is it a small value to what it should be? Is it a really high value? So the answer has to kind of make sense. Trying to have a general idea of what the answer should be before you even start assumptions. Right, let's go to the next one. A 750 kilogram coaster drops from 90 meters on a frictionless track. The braking section has a kinetic friction of this much. How far must it travel to stop? Interesting. So for this kind of problem, we need to go back to work. Okay, so we've got friction work. The friction is going to equal the initial energy. So remember, the friction in this case, I don't know if you remember the formula for friction, it's mu multiplied by the normal force. Okay, so I have to sort of just say a disclaimer here. You don't have to worry about this kind of calculation in the exam, simply speaking, because we don't have friction as part of this assessment. But I'm going to work this out anyway. So friction is equivalent to mu times normal force, which is going to equal 0.720 multiplied by normal force is equivalent to mass times gravity. So it's going to equal 750 multiplied by 9.81. 0.720 multiplied by 750 times 9.81. 5,297.4 newtons. So we've got the force. This is. That's the force. And remember, work is equivalent to force times distance. So what is work? Okay, because we need the distance. That's what we're looking for. How far must it travel to stop? We're looking for the distance. That's what we're looking for. We've just worked this out. What about the work? Well, the work is also equivalent to change of energy. Remember, W is equivalent to change of energy. What kind of energy do we have here? We've got mgh, which is gravitational potential energy. So it's going to equal change of energy in this case is equivalent to force times distance, and the change of energy is mass times gravity times height. So that's going to equal 90 times 750 times 9.81. So the change of energy is 662,175, and that is equivalent to the force, which is 5297.4 multiplied by the distance. So now I can work out the distance, obviously, which is going to be that divided by that. So it's going to be 125 meters exactly. Okay, let's keep going. Oh, these are some nice easy ones. A 52 kilogram person walks up 31 meters of stairs to a bungee jump. How much time does it take if the person uses 250 watts of power? So we've got a couple of formulas we need to know, but the first thing we need to do is how much time. So we need to work out time. So the first thing I need to know is how much energy did the person actually use to get to the top of the stairs, and the other thing I need to do is work out the time. So first step is, let's see, I can work out, right, let's see, work is going to be force times distance, which is going to be, since he's moving upwards, 52 times 9.81, because the force in this case is the mass times gravity, right? Times the distance, which is 31 meters. And there's a couple of different ways you can do this, right? So don't worry if you don't want to do it my way, you can do it a different way. That's all good. Whatever you're comfortable with. I've worked out the work. Okay, so I've got the work. So what do I do with it now? Well, I know that once I've got the work, and energy is going to equal, power is going to equal energy over time, or work over time. So both are interchangeable in this case. Just a second, please. Okay. Apologies about that. My daughter just walked in. Okay, so power is equal to work over time. We've just worked it out. So we know the power is going to be 250. So we've got that. And now we've got this. So we need to work out the time. So time, let's just rearrange it. Time is equivalent to work over power. Okay. So it's going to take 63 seconds. Okay, let's move on. A 0.1 kilogram ball has 0.5 kilograms meters per second, so that's momentum. What is the velocity? Easy peasy lemon squeezy. Momentum is equivalent to mass times velocity. We've got that, and we've got the momentum, which is 0.5. Therefore, velocity is equivalent to 0.5 all over 0.1. Just checking that I had everything in order. Now, I do want to say that this is the kind of question that you will get in the multiple choice. Okay, and you shouldn't spend more than sort of 30 seconds to a minute on it. Okay, let's move on. An object has 300,000 kilograms meters per second of momentum in the x direction and 400,000 kilograms meters per second in the y direction. What is the total resultant momentum? So, hello Pythagoras. Right, so here we go. So we've got 300,000 in the x. Okay, let's see where I am. Oh, nope. Not bad. Here we go. We'll keep that. So 400,000 in the y. Now we're trying to work out this guy here, the resultant. So that's going to be r is equivalent to the square root of x squared plus y squared, which is these two. So it's going to equal square root of 300,000 squared plus 400,000. Last time, I don't even need to work. It's 500,000. Sometimes it's just habit. You know, you try and check things in the calculator even though you know the answer. Right? So here we go. That's the answer to that. Right, moving on. 3 cars. What is the total momentum of the system? Okay, we need the total momentum of the system. We've done this before. We've got three cars that are traveling in different directions, and we need total momentum of the system. The first thing we need to realize here is that I can't simply just work out the momentum for each one and just add them. I need to work out the components of the momentum. So I need to work out the x and y components. So let's go and do that. So car A, the components of the momentum are, let's see, it is traveling in north direction. So I'm just going to make a small tiny diagram just to, oops, so, you know, I'm still getting used to this. Not bad. 1,300, and it's traveling at 15 meters per second. Okay, car B is over here, and it's 1,200, and it's traveling east at 17 meters per second. Whilst car C 900, and it's traveling at 45 degrees northeast. Okay, it's traveling at 20 meters per second. Okay, so that's the first step, to visualize it. Next step is to actually work it out, work out the momentums. So let's see. Momentum is equivalent to mass times velocity. Oh no, we're not there yet. It's going to be a while. Momentum is equivalent to mass times velocity. So what I need to do is multiply momentum by velocity. So, sorry, mass by velocity. So momentum here is equivalent to 19,500. But it's all in the y direction, yeah? So y is equivalent to 19,500, and there's 0 in the x. Okay, what about the next one? The next one's going to be 1,200 multiplied by 17, and so momentum over here is going to equal 20,400. Now the y is 0, there's nothing, it's not going up and down at all. The x, however, is 20,400. Now we need to work out the momentum here. The momentum is going to be 900 multiplied by 20. So that's 18,000. However, that's neither y nor x. Okay, we still need to work out the x and the y components of this. We've got the angle. So if I need to work out the y and the x, what I need to do is work out the opposite and the adjacent. So one way of working out the y is by going sine 45 is going to equal the opposite, which is y, all over the momentum. Oops. Remove that now, we don't need that. What we need is the 18,000. So all over the hypotenuse, which is 18,000. And so therefore y is equivalent to 12,727.9 kilograms per meters per second. Now the x, just so happens, is going to be exactly the same. I mean, the reason why I know that is because it's 45 degrees, so it's the same on both sides. It's an isosceles triangle. It's a right angle isosceles triangle. There. That's what we have over here. It's a right angle isosceles triangle. Both sides are exactly the same. But if you prefer, you can still work out the x the old-fashioned way. You can say cosine 45. Cosine 45 multiplied by 18,000. And that will give you exactly the same answer. So anyway, we've got x and y here. We've got x and y now. So what do we do? Well, I've got all x's and all y's. So now the next step is to add them all together. That's what I need to do. So that was step one. That whole thing was just step one. Now step two would be add all. Why is it so thick? add all x's and y's together to get a triangle, right? So x total will be and y total will be. So let's see, the x total is going to be 20,400 plus 12,727.9. So the x total is going to be 33,127.9. The y total, on the other hand, is 19,500 plus 12,727.9, and that's going to equal 32,227.9 kilograms dot meters per second, kilograms dot meters per second. We're nearly there. We've got a third step now, and I'm going to use a different color because I can. I'm going to use orange. I haven't used orange in a while. Okay. Oh, not 4, 3. So what I need to do now is draw the triangle. Well, it's just going to be fun trying to draw a triangle. Not bad. We'll go with that. So I've got the two vectors now. 32,227.9. I've got 33,127.9. And I need to work out the resultant vector, which is the total momentum of the system. Okay, so that's going to just be Pythagoras. A squared plus b squared equals c squared. A squared plus b squared equals c squared. That is c squared. So c is going to be the square root of x squared plus y squared. So, or I should say r, not c, because that's the resultant vector. That's what I've used. So that's going to be that plus 33,127.9 squared, square root of 46217.9 kg dot meters per second north east. That is your answer. Okay, so not so hard, it's just tedious, a lot of work, but that's the answer. Okay, let's keep going. You push a 22 kilogram cart with 6.5 newtons for 1.9 seconds. What impulse do you give the cart? Ooh, finally getting into impulse. Okay, so here, impulse is equivalent to force times time. So the way we write that is J is equal to F times T, or change of momentum, because remember, change of momentum is equal to impulse. So simply put, the impulse is going to be equal to 6.5 newtons multiplied by 1.9, which is 12.35. Now, what's the unit for impulse? Well, what's the unit for force? That's newtons. What's the unit for time? That's seconds. So the unit for impulse is literally just that, newtons dot seconds. Or 12.35 kg dot meters per second. Why? Because it's also equivalent to change in momentum, which is mass times velocity. So kilograms dot meters per second is also correct. So you can do that with that. A 0.45 kilogram basketball is hit with a force of 8 newtons for 0.6 seconds. What is the ball's change in velocity? Okay, so once again, we know that impulse is equivalent to momentum. So we have two formulas here that we need to think about. We've got change in momentum, which is equal to mass times change in velocity, or mass times velocity. And we've got change in momentum, which is equal to force times time. So if we work this out, we can work this out, okay? So I'm going to start over here this time, 8 times 0.6, and that gives me 8 times 4.2, right? kilograms dot meters per second or newtons dot s. So now that I've worked it out, I can go back here now and say 4.2 is equivalent to 0.45 multiplied by the velocity. And so I can work out the velocity. The velocity is going to be 4.2 divided by 0.45, which is equivalent to 4.2 divided by 4.5. 0.45. And that's going to equal 9.3. Wait, it's not 4.2, this is 4.8. Sorry. 10.7 meters per second. That's the answer. Okay. A 1.5 kilogram ball is moving at 3 meters per second. You stop it using a force of 9 newtons. How long did the force act? You really don't need this much space for this question. It's so simple. Okay, so once again, we know that momentum has two formulas, so it's going to be, impulse has two formulas. So it's force times time, as well as momentum is equal to mass times velocity. Change in momentum is equal to mass times velocity. So it's 1.5 times 3. I'm going to start over here because those are the components that I do have. So 1.5 times 3, and that gives me 4.5 kg dot meters per second. Now I take that over here. 4.5 is equivalent to the force, which is 9 multiplied by t. And therefore, t is equivalent to 4.5 divided by 9, which is 0.5 seconds. Okay? A ball hits a wall with 15 kilograms momentum and bounces back with negative 10. So that's the initial moment. Oops, no, not yet. 15, so that's the initial momentum, that's P1, and bounces back with this much, so this is P2. What is the total impulse delivered? Well, remember, impulse is equal to force times time. Impulse is equal to mass times change in velocity, but also impulse is equal to final momentum minus initial momentum, right? So we're using this guy here now. So impulse is equivalent to negative 10 minus 15, which is equivalent to negative 25 kg dot meters per second. Okay? Let's keep going. A 70 kilogram person jumps off a skateboard and pushes back with 210 newtons for 0.5 seconds. What is the skateboard's final velocity? Okay. So once again, we know that impulse, let's see, 0.5 seconds. So okay. So this guy here is talking about conservation of momentum. So we need to work out the momentum of the person. And once, do we? Let's work that. No, we don't. We just need to work out the impulse. And then if we divide it by, okay. So we've got momentum is equivalent to impulse is equivalent to force times time. So that's going to be 210, that's the force, and that's the time, multiplied by 0.5, and that's going to be 105 kg dot meters per second. I have the change in momentum. Okay? Now what I need to do is figure out what's going to be the speed of the skateboard. The speed of the skateboard is going to be mass times velocity. What is the mass here? Mass is not 70, that's just there to trick you. The mass is 5. Okay, that's the mass of the skateboard. So 105, oh, no, don't do that. 105 is equivalent to 5 times velocity. Therefore, velocity is equal to 105 divided by 5, and that's going to be 21 meters per second. Okay. I'm going to take a break before I tackle this problem here because we're going to need the break. I'll see you soon. Okay, hello again. And here we have a question that once again we're talking about momentum. A 1,250 kilogram car is moving at 32 meters per second when it crashes into another car moving at 25 meters per second. Now we've got a diagram to actually illustrate this as well. What is the final velocity of the combined cars? So that's the first thing we need to worry about. The second part of the question says how much energy is lost in the collision. So let's start with the first one. Okay, now I've also got, let's see. Okay, so part A is what we worried about. How much velocity what is the velocity of the combined cars? Now obviously we're talking about an inelastic collision where both cars have hit each other, deformed, and have become one mass. Okay, so the first thing we need to do is work out step 1, work out momentum for each car. Okay, so let's do that now. So momentum for the first car is going to be 1,250 traveling this way at 32 meters per second, and so the momentum is going to be mass times velocity, which equals 1,250 multiplied by 32, and that equals 1,250 times 32, 40,000 clean kg dot meters per second. Now the second part of the question, the second part, I should say, not the question, but this part here. We've got a car, oops, don't like that little dot. Back. Here we go. We've got another car, and this time it's 875, and it's traveling at 25 meters per second. So the momentum for this car is going to be mass times velocity once again. 875 multiplied by, now this is where we have to be careful. Now obviously it's going in the opposite direction, so we need to make this different. So we need to make this negative, okay, because it's traveling in the opposite direction. Now you could have made that one negative and this one positive. It wouldn't have made the difference at all, as long as you stay consistent. So 875 multiplied by negative 25, and that will give me negative 21,875 kg dot meters per second. Okay, so I've worked out the momentum for each car. What do I do now? So what I do now, step 2, is I want to work out the total momentum. Calculate total momentum. Now the way we do that is, of course, total momentum, total momentum is going to equal P1 plus P2. So it's going to be 40,000 plus the negative 21,000, so you could just go negative 40,000 minus, but I just like to do things the long way so students understand what I got it from. So total momentum is going to equal 18,125. No, don't do that. That's not what I wanted to do. 125. Sorry about the children in the background if you can hear that. Kg dot meters per second. So what do I do now? Finally, I have to do step 3 now, which is the velocity. Okay. Calculate velocity. What happened to red? Here we go. Calculate V. So we know that momentum is equal to mass times velocity, and we have momentum, so it's 18,125. That's the total momentum. Is equivalent to the total mass. Ooh, this is total mass, by the way. Okay, so what mass do I use here? It's total mass for both cars, because now they're one object, they're one mass together. So it's going to be 875 plus 1250, which is 2125. 2125 multiplied by the velocity, and therefore the velocity is going to be 18125 all over 2125. .53 meters per second. Okay? And that's going to be to the right. Now, the reason I know that is because it's plus, so it's positive already, so that just implies that it's going to the right, because we've decided early on that that's going to be positive and that's going to be negative. So I don't even have to say that. But if you put an arrow, that's always better. So it's 8.53 meters to the right. Okay, so that's the answer to that one. What is the final velocity? It's going to be, let me just, 8.53 meters per second. And I have to remove all of this now. Oops, there is a way to remove all of this. How do I do that? There we go. So I'm just going to write this there. 8. Sorry. Okay, now the reason why I wrote it here is because we need it for the next part. Now for the next part, how much energy is lost in the collision? Now remember, when two cars are colliding together, what's going to happen is they both have kinetic energy, and this is what it means here. Energy is never lost or destroyed, but what they mean here is how much kinetic energy is lost. So we're going to change that to kinetic energy just to make things clear. Okay, so what we need to do is step 1, we need to calculate total kinetic energy before. And in order to do that, I need to calculate the kinetic energy of both cars. So the first car, and I'm going to do it this way, kinetic energy of the 1,250 kilogram car is going to be half mv squared, which is equal to half multiplied by 1,250 multiplied by 32 squared, and that's going to give me a number 1,250 times 625 times 32 squared, which is 640,000 joules of energy. Now I need to do the same thing to the other car, so that's going to be kinetic energy of the 875 kilogram car is going to be 875, sorry, half times 875 multiplied by 25 squared. Now you might be thinking, well, hang on, it's negative 25. It doesn't make a difference because energy is not a vector quantity. So whether it's 25 or negative 25, if you square negative 25 times negative 25, it's going to give you a positive number. And so it doesn't matter whether you put negative 25 or 25. If you prefer, I can do that, negative 25 squared. It's still going to give me a positive number here, okay? So times 75 times 25, and that's going to equal 273,437.5 joules. So the total energy before is going to equal KE total is going to be the addition of both of these. Okay, so I'm going to use blue this time. 640,000 plus 273,437.5, and that's going to equal 913,437.5 joules. Okay, that's the total energy before. We've just worked it out. Now we need to calculate total energy after. Okay, energy after is going to equal, well, it's the same process, but this time KE is going to be for both masses. So it's going to be for 2125, which is both cars combined. Yeah? And that's going to equal half times mass times velocity squared, which is half multiplied by 2125 times, what is the velocity here? Well, lucky for us, we worked it before. Remember, it's 8.53. So 8.53 squared, and that's going to give us a number. And that is 77308.46. Just go with 0.5. We're working with such big numbers that it doesn't matter to go 2 decimal places. Okay? So now we still haven't answered the question. The question says, what is the energy lost? So don't forget, there's a third step here, which is calculate the energy lost. So it's not enough just to say that. So we need to go that's a lot of energy lost. So the energy lost is going to be energy after almost French there, lost. And that's going to be KE after minus KE before, which is 913,437.5 minus 77308.5, and that equals 836,129 joules. That's how much energy was lost. It's a big number, but obviously must have been quite a horrendous crash. Most of that energy is lost as deformation energy. Okay, so there'll be sound, heat, as well as deformation. Okay, let's go to the next one. A 9 kilogram ball is moving to the right at 14 meters per second, while a 12 kilogram ball is moving to the left at 5 meters per second. If they collide head on and stick together, what is their final velocity? So this is very close to the previous problem. What we need to do first is find the momentum of each ball. So the way I like to do this is visualize it. So 9 and then 14 meters per second, and the next one is going to be 12 moving at 5 meters per second, and so I can calculate the momentum, which is going to be mass times velocity. Remember, the velocity is opposite directions, so 9 times 14 is going to be 126 kilograms dot meters per second, while this one's going to be 12 times negative 5, because it's in the opposite direction, so it's going to be negative 60 kilograms dot meters per second. And so the total momentum is going to be P total is equivalent to P1 plus P2. We'll call this P1, we'll call this P2, which is going to be 66 kilograms dot meters per second. That's because that's 126 and that's minus 60. So what do we do with that now? There's step 2, and step 2 is going to be find velocity of both objects combined. P is equal to mass times velocity. We've got P, which is 66. Let's use green. 66 is equivalent to, now we get to use total mass once again. So the total mass is both balls combined together. That's because they are one entity now. So 21 kilograms times the velocity. Therefore, the final velocity is going to be 66 divided by 21, which is 3.1 meters per second to the right. But you don't have to do that because positive is to the right anyway, because we've already defined it here. Negative to the left, positive to the right. But if you draw an arrow, it's always better. Okay, let's go to 30. nearly there. An 82 kilogram football player is running north at 3.1 meters per second, and a 96 kilogram player from the other team is running west, which is negative x direction, at 2.4 meters per second. Now, because the question defines positive as x and negative as negative x, or negative x direction is west, that just makes things a little bit easier. They collide and stick together. What is their combined speed immediately after the tackle? Okay, so we've got a diagram here as well. I'm just going to use the diagram, by the way, just because it makes things easier. And I'm going to draw a wee circle here, and I'm going to say 82 kilogram for that one. And I'm going to draw another circle here, and I'm going to say 96 kilogram for that one, 96 kg. And so now I can work out the momentum, and I can just do that right there actually. So momentum for this is going to be 96 times 2.4, which is 230.4. And the momentum of this is going to be 3.1 times 82, which is 254.2. So now I've got the two momentums. What am I supposed to do with them? Okay, well, we've got a triangle, which is great because that's what I wanted. So what I can do is I can draw the triangle. Okay, so I've got, whoops. No, okay. Try and see if I can get this right. Here we go. Yeah, that's better. And then, not quite. Getting there though. Oops. Here we go. Not too bad. That'll do. Right. So I'm gonna label this. That's 230.4, and this is 254.2. And what am I being asked to do is I'm being asked to calculate this guy here. Okay, that's close enough. The resultant. So first I have to find the resultant vector, right? That's the first thing I have to do. And then once I find the resultant vector, I can calculate the velocity, which is what they're asking for. So that's going to be a squared plus b squared equals c squared. And so therefore, r is going to equal the square root of 343.1 kg dot meters per second. That's what that is. And it's going to be northwest. Okay. Now, what do I do with this now? Now, step 2 is find the velocity. Since I've got the momentum, it's easy. So all I have to do, add the two masses together. Don't forget, the mass is going to be the combined mass, which is 178, multiplied by the velocity. And so therefore, velocity is equivalent to, let's go with orange, 343.1 all over 178. So 1.93 meters per second. So the two people have become one, and they are moving. Did I get this right? And they're moving at 1.9 meters per second, 1.93 meters per second. Okay, let's keep going. So we've answered that, we've answered this. We've got 2 questions to go, which is great. Okay, so what do we have here? we have to calculate the change in momentum. A 0.25 kilogram hammer strikes a nail at 7 meters per second and stays in contact for 0.0015 seconds. So that's just a striking it. What is going to be the hammer's change in momentum? And calculate the force between the hammer and the nail. So first of all, let's calculate the change in momentum. So in order to calculate the change in momentum, we're going to see what we have. What do we have? We have the mass, okay. We've got the velocity, so that's velocity, that's mass. We can definitely, and we've got time. So let's go with part A. Part A, change in momentum is going to equal mass times change in velocity, which is equal to 0.25 multiplied by 7, and that's going to give me a nice number. 0.25, what's a quarter of 7? 1.2, 1.625 maybe? 1.75 kg/meters per second. Okay, so that's the change in momentum. So I've worked it out. I've worked out the change in momentum, which is delta, whatever, delta p. So now I can calculate the force, because I also know that delta p is equal to force times time, and I have everything. I have 1.75. I got that because I worked it out from before, just there. And I've got the force because, no, I don't have the force. That's what I'm trying to find out. But I do have the time, because the question tells me the time. And so force is going to equal 1.75 all over 0.0015. And the force is going to be quite big. So the force is going to be 1166.7 newtons. Okay, down, but you don't have to worry about direction. So that's, oops, that's not part B, that's part A2, I should say. That's A1 and that's A2. So we still haven't, oh no, we have. That is B. Oops, that is B. Yay, done. Okay, and let's go to question 32. So here we have a question that talks about another collision. Oh, and obviously it's an inelastic collision, so two objects are stuck together and they're moving together. Now you really should know this, by the way. Okay, I know some students don't know this, but it would make your life so much easier if you do know that. Okay, alright, so let's go. What are we looking at here? We've got a car that's 1200 kilograms moving east at 25 meters per second, 1200. And then we've got another car where that is a pickup truck, boom boom boom, and that is 1500, and that is moving north at 20 meters per second. So the first thing we need to do is calculate the speed of the wreckage after the collision. The speed of the wreckage after the collision. So obviously I need to calculate the momentum and then find the whole momentum, like the momentum of both. And then I can use that to calculate the velocity. So the first step I need to do is this one here. So we're doing A, yeah? A, and I'm just gonna say A1, which means A step 1. And let's use red to calculate the momentum. So that's going to be 1200 times 25. And this is going to be 1500 times 20. And both of these will equal 30,000 kilograms dot meters per second. Okay, now what do we do with that? Well, next step, back to blue. Oh, back to blue. Blue. Here we go. Is we draw the triangle. Not bad, but I can do better. Maybe that's better. Anyway, so that's 30,000 and it's 30,000 on both sides. So now what do we need to do? We need to figure out the resultant vector over here. Oh no, don't, not yet. Here we go. We need to figure out this guy here. So how do we do that? Well, obviously it's a squared plus b squared equals c squared. In this case, we're trying to find r. So r is going to equal the square root of y squared plus c squared plus x squared, which is the square root of 30,000 plus 30,000 squared. Okay? And that is simply my trusty calculator, which I've had for 25 years. 30,000 squared plus 30,000 squared. That's a big number. Here we go. So r is equivalent to 42426.4 kg dot meters per second. So this here, what we've just found was the total momentum. Total momentum, which is this momentum over here. Okay? So now what do we do? Now what do we do? Now we go over here and we say that momentum is equivalent to mass times velocity, which is equivalent to 42426.4. The mass. What mass do we use? What mass do we use? What mass do we use? We use total mass, which is both cars combined. So that's going to equal 12 plus 152,700 multiplied by the velocity. And therefore, that's what this means, by the way. I've had a few students ask me what this means. That means therefore, okay? Therefore, velocity is equivalent to, yay, coffee. Therefore, velocity is equivalent to 15.7 meters per second. Great. Are we done? Not quite. Now we've just answered A. So what we need to do next is answer B. We still have B. How do we answer B? B is the angle. That's the easiest thing. We need this angle here. Okay, so how do we do that? Well, green? Yeah, green. Theta. Is that green? Okay. To calculate theta, we need opposite over adjacent. So remember, so ka toa. We're going to go with this guy because we have the opposite and the adjacent. So it's going to be shift tan theta is equivalent to the opposite over the adjacent, which is 30,000 over 30,000, which, by the way, is equivalent to 45 because they're exactly the same anyway. So 45 degrees north east. If you don't put the northeast and you just say 45 degrees and you draw an arrow, that's fine too. Okay, just make sure you draw an arrow and show us the direction. And that's it. I mean, it looks like a lot, but it's an important question. It is an important question. Okay, that's your tip of the day. Very important question. All right, let's go and try and do some MCQs. MCQ practice. Let's have a go. All right, so once again, try and do these on your own. Pause the video, try and do it, and then check your answers with me. So let's go. A 3.2 kilogram ball moves at 7 meters per second. What is the momentum? Momentum is equivalent to mass times velocity, which is equal to 3.2 times 7. Excuse me. Sorry, sometimes I just get carried away. So 22.4. Next, a 4 kilogram trolley is traveling at 3 meters per second, sticks to a 1 kilogram block at rest. What is the final speed? Okay, so this one is a little bit tricky, okay, because what you need to do here is figure out the total momentum before, and then do momentum after. So momentum before, what we have is here we go. We have a 4 kilogram trolley, 4 kg, traveling at 3 meters per second, and it's hitting a 1 kilogram trolley that is not moving. So the total momentum here is 12. And we know that the momentum after is going to be 12. Momentum before equals momentum after. In case you guys didn't know that, momentum before, momentum before equals momentum after. And so we have, but this time, remember, they stick together. So it's going to be 5 kg. And we're trying to figure out what V is going to be. So it's going to be 12 divided by 5, which is 2.4. Next, different color. A 30-gram bullet leaves a rifle at 250 meters per second. What is the kinetic energy? Change 30 grams to 0.03 kg. Because you divide the 30 by 1,000. So 0.03. Oh, sorry, I have to write the formula. You don't have to obviously show any workout during MCQs, but it's just good practice. Just so when you're doing the revision at the end of the exam, after you finish answering everything, you know where you went wrong. Also, the way to do it is, if you can, don't look at the choices at all. So look at the question, solve it. Don't even look at the choices. When you're revising as well, try and cover your answer. So you're doing it like in the exam. Once you've done the question, cover it up so you don't look at your answer, so it doesn't mislead you. Do it again without looking at your answer. All right. Anyway, so half mv squared, obviously, which is half times 0.03 times 250 squared, and that is equivalent to 938. Now you might have noticed that it's going to be 937.5. This is the closest. Go with the closest. Okay. Different color. Green. A 6 kilogram toolbox is lifted 3 meters. How much gravitational potential energy does it gain? Okay, so GPE is equivalent to mgh, which is equivalent to 6 times 9.81 times 3. So 176, I think. 6 times 9.81 times 3. 176.6. Again, that is the closest. An 80 Newton force acting at 30 degrees pulls a sled 6 meters. How much work is done? Okay, so blue. And we're going to go with work is equivalent to force times distance times cosine theta. So that's going to equal 80 times 6 meters times cosine 30, which is equivalent to 80 times 6 times cosine 30, and that is equal to 415 joules. Okay? Yeah. Okay, we've got 20 of these, just so you know. If you're wondering how many multiple choices we have, we've got 20. It's good practice. A motor does 900 joules of work in 4 seconds. What is the power? Okay, so just remember, change of energy is equivalent to work. So power is equal to work over time, or change of energy over time. So you've got that. You've got 4. So power is equivalent to, I'm just doing it the long, boring way, just so people know how I got it. That's work and that's time, which is equivalent to 225 watts. And watts is the unit for power. Next, we'll go with black. Which of the following is a correct unit for momentum? There we go, easy peasy. A 1,200 kilogram car accelerates from 15 to 25. What is the change in kinetic energy? Now, here's the thing about these kinds of questions. Make sure you solve it for 15 and you solve it for 25. It doesn't work if you go 25 minus 15 and you go, oh, it's 10. So let me just do this. Half times 1,200 times 10 squared. That doesn't work. Okay, the reason why it doesn't work is because it's squared. Okay, so what you need to do is you need to solve it for at 15, meters per second, and then you go half times 1,200 times 15 squared, and then you go at 25 meters per second. Let me just remove this. It equals half times 1,200 times 25 squared, and then you go this minus that. Oh, what am I doing? Come on. Okay, so it's going to be, for me, 0.5 times 1,200, which is 600 times 25 squared, minus 0.5 times 1,200 times 15 squared. And that is 240,000. Okay? Orange. Which factor does not affect objects' gravitational potential energy? Well, GPE, that is gravitational potential energy, is equivalent to mass times gravity times height. Mass, gravity, height. Mass, gravity, height. So what doesn't affect it? This guy here. Okay, at 30, back to blue. A 30 Newton force acts for 0.5 seconds. What impulse is delivered? Impulse is equivalent to force times time. Also, impulse is equivalent to mass times change in velocity. And also, impulse is equivalent to final momentum. Oops. Final momentum minus initial momentum. So all three. I've got force, which is this guy, and I've got time, which is this guy. So I'm going to use this formula. Okay? 30 times 0.5, which is 50. Next. Which change produces the largest change in momentum? Largest change in momentum. Of course you would do that. Of course you would. Here we go. Largest change in momentum is going to be, let's see, you got to do the multiplying, because change in momentum is equal to mass times velocity. So it's going to be, just a second, got this thing that I use, and it just makes my job a little bit easier. Okay, here we go. So what I need to do is I need to calculate the change in momentum. So I got to multiply 3 times 0 here. So it went from 0 to 12. Because it's 3 times 0, which is 0, and 3 times 4, which is 12. In this case, it went to from 5 to 5 times 1, which is 5. 5 times 3 is 15. And here it went from 12 to and here it went from 0 to 5. So the difference is 12, 10, 6. We're all not looking at the difference. It doesn't matter, that's negative 6. And here it's 5. So the biggest one is A. Okay? Alright, 12. A student carries a 7 kilogram bag horizontally at constant height. How much work is done? 0. Because it says horizontally. So the work was done when they were carrying it, but then in the horizontal direction, there's none. A 0.4 kilogram, I'm still going to use red. A 0.4 kilogram ball rebounds off a wall with the same speed but opposite direction. What happens to its momentum? Okay, same speed, opposite direction. It reverses direction. Okay, that's all. Because let's assume, for example, the speed is 5 meters per second. And over here, the speed is, and rebounds. Okay, so negative 5 meters per second. So it went at 5 and came back at negative 5. Then what happens to the momentum? Look, 0 times 0. Oh, sometimes I think too fast. 0.4 times 5. And here it's 0.4 times negative 5. So obviously this is going to be 2, while this is going to be negative 2. So it just reverses direction. Okay? Orange. Is a spring with this K value is compressed at 0.15 meters. How much elastic potential energy is stored? So it's going to be EPE is equivalent to half KX squared, which is equivalent to half times 200 times 0.15 squared. Don't forget the squared. So it's 100 times 15 squared. 15 squared is 225 times 100. So 2.25. Okay, next, green again. A 3 kilogram rock falls 8 meters. What is the speed at which it impacts the floor? GPE is equivalent to KE in this case. So it's going to be 3 times 8 times 9.81, which is GPE, MJH in this case. So this is M times G times H. And this is going to be half times, not K, half times M times V squared, yeah? So all of this is equivalent to half times M, which is 3 times V squared. Therefore, V is equivalent to, and then you got to do some calculations here, 3 times 8 times 9.81. That is 235.44 is equivalent to 1.5 times V squared. So therefore, V is equivalent to the square root of 235.44 all over 1.5. 12.52. 12.53 meters per second. So which one is it? It's this. Okay, it rounds up. Moving on. A 20 kilonewton rocket thruster fires for 0.8 seconds. Okay, so that's force. Don't get scared when you see these. That's force. You just got to realize that's newtons. I will not be using kilonewtons, by the way, but just letting you know, that does mean 20,000 newtons. For 0.8 seconds, that's time. On a 500 kilogram module, that's mass. What is the change in velocity? All right. So remember, we are looking at momentum. Change in momentum is equivalent to force times time. And that is equivalent to 20,000 times 0.8. And then once I do that, I can, so that's 16,000. Now what do? Now I go here, equals mass times velocity, and I've just worked that out. 16,000 is equivalent to 500 times V, and therefore V is equivalent to 20 and 10, 30, 32? 32 meters per second. Okay. Red. A crane lifts 250 kilograms mass, 5 meters height. Time. What is the average output? Okay, so I can work out the change in energy, and then I can divide it by time. I've got the time, and I've got mass, and I can just do MGH, couldn't I? MGH. So that's going to be 250 times 9.81 times 5. 250 times 9.81 times 5. 1262.5 joules. And the time is 8 seconds. So all I have to do is go power, and power is capital P. Okay, so that's how you write power. Equals change of energy or work over time, which is equivalent to 262.5 all over 8. 1,532, which is closer to 1.5. Okay? That's how you do that one. Next. Orange. A 60 kilogram skater changes velocity from -2 to 3. What is the impulse experienced? So remember, impulse is also equivalent to change in momentum. So final momentum minus initial momentum. So all I have to do to find the momentum is go, well, final momentum is equivalent to 60 times 3, while the initial momentum is 60 times -2. So that equals 180, and that equals -120. And so what's the final? It's 180. What's the initial? -120. And so it's going to equal 300, because 180 minus -120 is equivalent to 300. So a bit of a tricky one, but if you do it the way I did it, you can't go wrong. In a perfectly elastic collision, which quantity is always conserved? Perfectly elastic. So that means they bounce off each other completely. And in this case, okay, momentum is always conserved, but kinetic energy is conserved as well in a perfectly elastic collision. Because what it means in a perfectly elastic collision is that the objects have bounced off each other and there's no deformation, there's no sticking together. Mechanical energy is the combination of gravitational potential energy, and so there's none of that. But actually, believe it or not, momentum and kinetic energy are both conserved. So this question is kind of wrong. But anyway, both of these are correct. Now I want to check that. Pause 1 second. Yep, so that is perfectly correct. So it is A and B. Of course, in the exam, you'll never get a question with two answers. So that's just an anomaly there. Okay, next, orange again. I like orange. A cyclist maintains an average power of 250 watts for 40 seconds. How much work is done? So power is equivalent to work over time. If we have 250 and we've got 40 seconds, then how much work is done is going to be 250 times 4, which is 10,000. 10,000. Okay, well, there we go. That was it. That is your physics revision as far as I'm concerned. You are going to be perfectly okay. I would like to say thank you so much to my amazing students this year. You have truly made it a wonderful year. I really enjoyed it. And I hope to see you again in grade 12 next year. And all the very best for your physics exam and the rest of your exams. And have a wonderful holiday. And please stay curious and continue your learning journey no matter what. Bye.